Yesterday we were talking about the line source, okay. And we talked about infinitely long line source, okay. And the C was, what was that, 2 times small q sigma z times u exponential, what was that, z square by generally generally from like national highways, okay, or like even like things like GT road, what is passing through, this kind of thing formulation can be applied. But if you have the road where you have the quick turns left and right and things like that, yeah, then it becomes difficult. But for the large national highways, you can apply this particular model, because you see here the most of the vehicles are continuously moving one after the another one, and this kind of thing can be applied. But if you have something like very packed urban area where the zigzag crossings and things like that, and then naturally we would prefer it to model that as the area source, okay. But these are the large national highways, you can certainly, that will be difficult. You see, the thing is the closed form solution that we have got sometimes is not applicable on very special situations that we have not talked about. The model which we have talked about so far is generally applicable in the flat terrain, okay. And there are ways and means to define what is a flat terrain. See, obviously when you say flat terrain, then what is a flat terrain? Right. So that slope should be less than 1 by 16 or something, so that defines as a flat terrain. There is a way to define if the terrain is flat. If you have like a valley or a mountain or things suddenly dipping and things like that, there are certain, you can still apply this model to a certain approximation. But if situation is still more complex than what we can represent through this one, then what we do is what we call as physical modeling, okay. Then you create such situation in the wind tunnel, okay, because you can't write mathematics for such features, okay. It's not easy to write the mathematics. Then you do the experimentation in the wind tunnel, okay, and then you can really scale down the objects like this. You can make the buildings, you can make the hill, you can make the valley, and you can make a source in there, and then you can do the measurements as how the concentration is changing, okay. You can change the wind speed, you can change the turbulence, you can change the mixing height in the wind tunnel, and then we do the physical modeling. Certain things where we cannot apply the model because these models are again based on certain assumptions, and one of the important assumptions is that the terrain is flat, okay. So if terrain is not flat and it has its own complexities, then we go to something called physical modeling, okay. But that we are not discussing in this course, but definitely wind tunnel are very extensively used to cover or to understand the dispersion under the complex conditions, okay. All right. As was pointed out by one person later, suppose this is your road and this is your wind direction, make an angle phi. So this phi should be in the denominator, okay. Probably we wrote in the numerator, but this should be in the denominator for obvious reasons. If phi is 0, what is the concentration? almost it will say infinite. Okay. So, you can't use this particular formulation if sine is if the angle is very very small. Okay. What it really means is if the angle is very small, then your wind direction is like this, right? And then what is your x, if the wind direction is like this, what is your x direction? Is like this. Wind direction, see, you will never make a mistake as long as you understand in all the Gaussian kind of models that we have discussed, my wind direction is my x direction. I say it again and again, okay? And the moment the wind direction change, it means my x direction is changed. Okay, don't forget that. So it means in a way I am calculating the concentration on the top of the vehicles, and then you expect concentration to be very very large, like you are just, if you go over the road just 2 meters and you are just onto the vehicle, then concentration is really large. So to avoid that thing, that angle should be generally less than about 20 degree or so for this to be really be very very valid. Should be more than 20. Okay. If it is very low, then you get very high concentrations. Okay, we will stop these discussions here, but just see where the sin phi appears. Okay. I want to do something using that formula again. Now, thing which we have not discussed so far is the maximum ground level concentration. So, many times we are interested what is the maximum impact, okay, where will it occur, how much will be the impact, and if I can take care of the maximum impact, my life is fine. Okay. So, many times we want to predict what is the maximum ground level concentration and where it is and how frequently it can occur. So, all questions we have to answer. So, for doing that one, if you see our, what was our equation was, I am going back to our original model. What was that exponential? Minus? Okay. If I am saying the maximum ground level concentration, it means y I have to assume as 0. Okay. As I move away from the plume center line, my concentration will drop off. So, to do that one, I will take that y equal to 0. So, I will not even write the term containing y. Okay. What was that? H square by obviously I want to find out the maximum concentration with respect to my downwind distance. Okay. So, I can differentiate this function with respect to x. Okay. And what are the things which are function of x here? Sigma y, right, sigma z. Is h also function of x? Although we have not talked about, but you can think, if you want to make the things very complicated, then h also will be function of x, because you see many books they talk about, the advanced books. Okay, you have this one, then this is my x, my h is constantly changing as x, is only after certain distance of the x this kind of stabilizes, the h stabilizes. Okay. But here h is different, h is different, h is different, h is different. So, some people whom you want to really do the things very precisely, then they would like to take this as the function of, even the h as a function of x. Okay. And in more sophisticated models, this is taken this as a function of x. But for simplicity, we may not really do this one. And
this distribution is not constant, it will change over time. Even in a day, this function will change.
okay, all right. Will change under what condition?
So, like say for example, if you take this monkey walk,
Yes.
where every day the profile of this
Fine, fine. What could be the primary reason why the delta H could change? Atmospheric stability. So at least I will say this thing is I am writing for a stability, for a particular stability. When you do that one, if the stability is changing, you want to compute hour to hour, you compute hour to hour concentration. That you compute hour to hour concentration. What will happen? Okay, you are saying in the first hour the stability was C. Okay, then you are computing it for C. Okay, you can't say, well, you want to just do work for now 1 hour and you want to extrapolate for 24 hours. You cannot do that one. So you will have to do, if you want to do the changes hourly concentration that is changing, okay, then you have to consider the hourly change in the stability, hourly change in the wind speed, hourly change in the effective.
Nobody can predict what will be the condition 1 hour after this time.
No, you cannot predict, but you can, with your previous background data, you know that in general what will be the stability of the particular hour of the day.
Then we will be increasing our errors.
Yeah, uncertainty is always there in the model. Uncertainty is always there in the model. In fact, any model you take, okay, you talk about the water quality model, you talk about the groundwater movement of model, the uncertainties are there. And then uncertainties, if they change, then they change. The model is still, you have to account for that uncertainty, and you say, okay, this concentration could be plus minus this particular thing. Okay. Yes.
This kind of scenario is considered
Yes.
we consider ground level it's 4 3 meters. The stability conditions there are totally different from what we observed.
Okay. See, at the ground level, the plume which is being affected, okay, plume for the, which is subject to dispersion. There is nothing happening here. This is what is the thing which is happening. So this stability, we assume that stability above this one is the main cause of the dispersion. Okay, and then dispersion, this dispersion may cause impact onto the ground level. See, eventually what will happen if I draw another picture. The plume is traveling and then it comes like this, then it will come like this. At some point, you see the concentration will start increasing. Okay, and what is the plume in general? The center line of the plume is affected by the stability which is there, or the conditions which are inside the plume. So then we see the impact of this dispersion or this expansion of the plume. What will be the impact onto the ground level? This is what we are seeing. Okay, suppose this was you say there was some wind speed or some friction here, that may not affect this one. Okay, so that is how we account for this one. That, and stability, you see, I mean, what you may be saying that there is an inversion layer here underneath this one. Then the modeling can be a little different. Okay, but you see here in general, okay, that is why even it is more important to do the calculation hour to hour. Okay, but again sometimes you just want to get the 24-hour average. So then you can even average these things for 24 hours. Okay, and then we will see one example hopefully when you can find out even the annual concentration. Okay, the annual mean wind speed is like this, annual wind direction is like this, and the frequency of the wind direction is like this, so that you can even account for the annual levels, and you say mean annual concentration will be like this. And in fact you will be surprised that mean values are sometimes more comparable to instant values, because mean values sometimes, of course you write the physics, you write the mechanics of this one or the mechanism of this one, but at the mean values many things cancel out from each other. Okay, and which we do not know sometimes, and then we are still happy. So always remember the mean values will probably match better than your instant values. Okay, but it is true that you can do it for 24 hours, and if you want to get a better accurate results, then you model hour to hour. You supply the data to the computer, because simple calculations we can do onto the board, but you want to do a more precise, more accurate measurements or concentration predictions, then you have to use the computers, supply the data, every hour what is wind speed, every hour what is the wind direction, every hour what is the stability class, every hour what is the mixing height, and then you can use the model and things like that. And then of course at the you want to find out the 24 hour, you have the 24 data of every hour, take the average of that. Okay. So I am saying whatever is the stability, but we are doing it for a particular stability. It may be A, B, C, D, E, F. Okay. So let us say whatever is the stability, so I can differentiate with this one, and then you find these are the functions of x, right, function of x, what else, again the function of x. Okay. If you differentiate this one, and I can put this equal to 0 to find out the maximum concentration. Okay. So this will be, I am writing the final form, you can see for this one yourself. Something like this. And I am not considering, for simplicity, I can write the another expression for dH also if I take h as a function of x. But just for the simplicity, let us not get into those sophistication for the time being, and I can put this equals to 0 to find the dH by, I am not considering that. I am not considering that h is a function of x, okay, but you can consider it if you like, okay, because after certain value of x which may be of interest to me like 500 meters or so, then this particular thing will not be the function of x. Okay. What will happen to the exponential term? Can someone, have we considered that or not in this one? This is equal to 0, so that term will come everywhere, right, and that is equal to 0, so that I can take the common out and get that one out. Okay. You can try this one doing it. Okay. If you recall, I gave you the thing that sigma y they were related to x in this form, okay. And let me again tell you that many people have come up with different kinds of forms, okay. Not that this is the final form. Essentially you had those graphs, okay. They have fitted some particular equations to that graph, okay. So I can put in place of sigma y, I can put this sigma z equals to this one, and then differentiate this one, okay. And then finally what you will see is that when you equate this equal to 0, so this condition that comes out to be, okay, that sigma z equals to for okay. I am giving you the final answer, but I am giving you the final answer, okay, to save the time. But when sigma z equals to h by square root 2, that is where you will get the maximum concentration. Okay. What it means in the physical sense. The h is fixed, right? Sigma z is changing with respect to this one, right? A situation will come where your sigma z, which is constantly changing with x, where the sigma z will be equal to h by square root 2. There will be some distance. Okay. Let us make it another picture. We will make a slightly different kind of picture. Let us just look at the physics part of it. Where you expect maximum concentration to be? Somewhere here, right? Because the plume is almost touching there. Okay. So, what condition it tells you is, and you here you will say the sigma z is changing because sigma z is function of x. So, the situation, the place, the x where sigma z has increased to such a level that it is equal to h by root 2, that is where you are likely to get maximum impact of an elevated source. Okay. Maximum impact of an elevated source. So, this may be I am just telling you that this situation may be somewhere here where sigma z has become equal to, what is 1 by square root 2 is 1.41 and 1 by 1.141, 0.7 something, okay, good, 0.7 something, alright. So, you see here that where sigma z, which is constantly increasing with respect to x, is nearly equal to, somebody said 0.7 or something, so I will write that number. There are many questions actually. Is the maximum ground level concentration, it will vary depending on what stability I am talking, yes or no? Yes, right? Because sigma z is function of stability also. So, okay, if my stability is A, my maximum ground level concentration will be something else. When it is B, when it is something else, C it is something else. Okay. Now, you have to tell me, if this is a situation, how can I find out the maximum ground level concentration and the location where it will occur? That is the question. Okay, how do we, what initially what we know? We know the sigma z now, right? Sigma z is very simple. H we have estimated, now we know the sigma z, and as it has been suggested that we go to the graphs, okay, the Turner graphs for sigma y and sigma z. Not sigma y, first we go to the sigma z graph, okay. Then we go to the sigma z graph. This is your x, this is sigma z, and the graph, if you recall, there was something like this. Very poorly drawn, but you can remember what the graphs were. So, suppose my condition was C, okay. Suppose my H was equals to 100 meters. Example, let us say we will do little thing, small thing, that you can calculate H, okay. That was your physical stack height plus delta H, right, okay. So, my sigma z for maximum concentration will be 70 meters, right. I go on to here and strike 70 meters, right, and my stability was, let us say, C. So, this is my distance where maximum ground level concentration will occur, right. Do everyone agrees, right? Okay. Now, you know this distance, and we can call this point as, this distance as xm, okay. Now, it should be very simple for you to find out what will be the maximum concentration. Now what you have been able to do is you have been able to find out the distance at which maximum concentration will be there. Okay. And once you know where it will be, now it is simple calculation to find out what is that concentration. Okay. So with this XM, you will go to your graphs of sigma y, okay, and then now go in the reverse direction and find out the value of sigma y, right, clear? And then you can fit in the value of sigma y, sigma z, you know, sigma z you know, and you can find out the maximum concentration. Okay. But to find out the maximum concentration, you have to do this exercise for A, for B, for C, for D, for E and for F. Okay. Because you want to really find out the worst scenario, then it can be A, it can be B, it can be C, it can be D, or it can be E or F. Okay. It will be different for different stability and different set of value of u, right. If you have one value of stability and one value of u, you can say under this situation this is the maximum impact, right. But stability will change hour to hour, as been pointed out. The wind speed may change hour to hour. So that is what our maximum concentration can be very variable depending on what stability and what you have. If that is clear, I want to get to on something which is still more important and still more interesting to note. If you recall, our H was H plus delta H, which was nothing but H plus, correct me if I make a mistake, what was that, 2.15? 1.5, okay, minus 3 P Ts minus Ta by Ts times D. Okay. If my u is playing a role, okay, what you can say, what the first thing I wrote was stability. Let us say we are not talking about stability, but u is certainly playing a role, okay. But you see here the contradiction, and really pay a little attention here. My C, if you look from this picture or this equation, C is inversely proportional to u, okay, from 1. C is inversely proportional to u or proportional to 1 by u. So more is the wind speed, okay, less is the concentration, right. This is what immediately when you look at this equation, that is what you are going to say, okay. But don't forget, this equation 1 has the built-in feature of equation 2. Where is this one? This delta H is somehow appearing here, right. Agreed? Okay. Do you still agree with the statement, or there is more complexity involved than this writing a simple statement like this? Much more complexity. Okay. It is not a complete picture, because if I take this whole thing here and put it in this one, then I am also finding u again, right. So the picture is complex. So u is not as simple as it appears, that C is inversely proportional to u. Okay. So and what you see here, if I plot this one, only this equation, then you have the C and you have the u. Okay. You might find that you may, as the u is increasing, C drops down. Okay. This is what is something like this, right. Okay. what will happen to my delta H if U increases? My delta H will speak out. I want you to speak. Delta H will decrease. Okay. Once my delta H decreases, my H decreases. If my H decreases, okay, then the concentration will increase because negative was exponential. Okay. It means what the U has done, one side U is saying that concentration will drop as U increases, but my another another term which is in the product tells you that, well, concentration may increase. If you increase the U, concentration may not decrease, okay, but it may increase. So if I somehow plot only this function, then you may find that as the concentration increases, then you will see as if U is increasing, the concentration may increase because of the U being there in the exponential term, which has come by virtue of delta H being considered. Okay. So what you will find that a maximum concentration may occur at some particular U, right. So U is not as simple term as we thought. Okay. U will be, there will be a particular wind speed, okay, for any given stability where the concentration may be the maximum, and such wind speed where we call it UC or U critical. Okay. So let us say what is U critical. So what do we do? I mean, we are all the time, what we are interested is that where is the maximum concentration that will occur. Okay. But what I don't know is that critical wind speed. Okay. So although there are many formulations that have been developed, okay, where you can find out mathematically as to where the concentration will be there, what you need to do is that you differentiate this one again with respect to wind speed, right, okay, and find out this thing and put the formulation for the maximum concentration and things like that. We will not do that one, but at least you got the feel that, well, there will be or there can be and there is a critical wind speed where the conditions can really be very, very bad, okay, and that is what sometimes we are interested in. So suppose you are planning a power plant or a refinery or a sulfuric acid plant, then you want to say, well, how far, what will be the maximum concentration under any given conditions, you know. As somebody said, well, you don't even know what is going to happen the next hour, but if you know, if you can find out the critical condition, okay, this is almost like predicting the global ever maximum concentration, because this is not based on the measurement. U critical, is it based on measurement? It's not based on the measurement, right. You can find out the critical wind speed whether the condition may occur or may not occur, okay. And this thing I will make it more clear to you that how in practice, how in actual we try to find out the maximum ever global concentration because of an elevated source, okay. How it is actually done in practice. Okay, if I can use the terminology, worst condition situation. I do it by trial and error. Okay. There are ways you can do without trial and error also, but one of the simplest thing is to do by trial and error. And what you do is make a table. Okay. Okay, what I want to do is I take some wind speed. Okay. Suppose I took the grid of wind speed at 0.5, 0.8, 1.2, 1.8, 2.5, 3.5 or more number in meters per second. From here, Q is known to me. A power plant is there, refinery is there, whether it is existing or proposed, right? If the refinery is going to come, I know about H. Okay. I know, first of all, I know physical stack height. They are going to provide a stack height of 100 meters, let's say. This is fixed, right? Delta H can be variable. How delta H will be variable? We'll see. The pressure can be variable, okay. But this variation again may not be so much because it's about close to 1000. This is a parameter which is fixed. They know that the temperature of the exit gases will be 100 degrees Celsius. TA could be variable, okay. This diameter is fixed because they have designed the chimney already. So this TA can be variable, this is fixed, and Vs, the exit velocity, is fixed because they have designed their ID fans and FD fans and what velocity they are going to push the things out. So this is fixed. The variables are this, okay. And then you see here, when will be the situation, when will the delta H will be small? When TA is large, okay, because the difference, higher is the difference, higher is the H. So criticality will occur when TA is high, right? When in the summer conditions, so you can assume this to be high, like in Indian condition, the ambient temperature you can take as a 40 degrees Celsius. So in a way I got this one fixed, this one also is fixed, okay, nearly 1000 millibars or something. So what is not fixed really here is the U and the stability, okay, and which by virtue of this, you know, the matrix or the double array, I am varying both of these things. I am varying what both? I am varying the stability and I am varying the U, okay, and then I can fill these little arrays as you see them, okay. So what I can do is take this stability A, okay, and what is another important thing is I have not gone to a meteorological office to get any data. Have we gone anywhere? Have we gone to the airport or something? We have not gone to the airport to collect any data. We assume, suppose if the situation was A and if this was 0.5, what will happen, right? We are not requiring any data from anywhere except the data from the plant, okay. Those data are fixed, okay. You see here again I repeat that we don't have to run to do the situation, to find out the condition, worst situation, I don't have to go collecting any meteorological data. Okay, clear? I know I have assumed the condition, suppose the conditions were A and the wind speed was 0.5 meters per second. Okay. These two things are fixed. Can I find out the maximum ground level concentration for stability A and wind speed 0.5? Right? Clear? I can write some number here. Okay. And I can ask my computer to do the same calculation for stability B. Okay. And or let's write here, if you like, we are talking about C max A 0.5, right? Okay. Then the concentration, and this is what? This concentration is what? This concentration is the maximum concentration for this situation. And how we got the maximum concentration? We have implied sigma z when sigma z is 0.5 h. So this is already maximum concentration for the condition this. So I can also find out Cb 0.5 and so on and so forth, Cc 0.5. Okay. And just to give you a little feel, suppose I want to say here, so then if you agree, I can write here Cd at 1.2. So I can fill this table. Okay. I can fill this table which is already maximum ground level concentration for the given condition. Simple thing. Now, I want to find out the worst condition. So then idea is the picking up the maximum out of maximum, right? Right? Picking up the maximum out of this maximum. So these are already maximum situation, and then you say, sir, what we found out that this situation, which let's say is Cb 1.8, was a situation where my conditions were reversed. Okay. You fill all these things. Okay. Just quickly write a small 2-line program to find out which block or which situation is giving you the maximum concentration. Okay. Even you can do it manually. All right. So what we can say, C max under the worst conditions or under worst ever condition, okay, if I can use a word, will be, because out of this table which already had the C maximums under the situation, suppose that came out to be, I am just giving example, that came out to be Cb. I think I have done a great job by saying that, well, maximum ever concentration that can ever occur because of some plant, okay, this will be like this. Very good prediction to do, and this is what we call this as, we call them as a screening model. We don't do any field work, but we can say that this can be the worst ever situation, okay. But the thing is, this may occur or may not occur, okay. This may occur or may not occur. But if it occurs, well, this scene can be as bad as what we have predicted, okay. And it is just an example, this will go beyond this. Don't misunderstand that we have to just consider 3.5, it has to go beyond this. And suppose you got the situations like this, you can fine tune this one by slightly increasing and decreasing this one. You can do at 1.725, 1.81, and like this. You can still do the finer gridding of this one and find out the maximum concentration that is likely to or that may occur, okay. But then the other thing is, now if I ask you, well, what do you think are the chances of this situation occurring? How would you do that? Then you will go back to your original data from meteorological office or from the airport and see the probability of getting the situation which is Cb 1.8. Now you go back and say, well, the probability of this situation occurring is really once in, let's say, 5 years. Okay, that with the historical data you can say It means this situation may occur once in 10 years, or you might say, well, such kind of situation may occur once in 2 months, well, then you have a problem. Okay. Or having done that one, you can go the other way around. Okay. You can, out of this situation, you can find out which situation under this thing is most likely to occur. Okay. The reverse way, and then you came out to be the situation which is most likely to occur as per the wind records which we have is this. Okay. Then you are likely to have the maximum concentration at this value. It is just matter of the information you have and you are interpreting them, making sense out of the things. You see, the calculations are simple, but you have to apply those things and get a answer which will help you make a right decision. Okay. This is all we are doing for some decision making. Okay. How much pollution is to be controlled, whether the plant can come up or not, where can it come, or will its maximum impact, can it be in the vicinity of the people where they live. So this kind of situation we do, and in this way you can even find out the worst ever possible maximum ground level concentration. Okay. Do you have any question? Yes, that will maximum. Yeah. So go ahead. That the probability you have to see that some situation will always, one of the situation will always occur. You are right. Okay. But sometimes situation can be this, sometimes it can be this. So what I am saying is, out of all the situation, try to find out the situation based on your records, which one out of this picture which you see 10 by 10 matrix or whatever, which is likely to occur with more frequency. Okay. Then you can design something for this one. See, sometimes it is very difficult to design something for worst scenario. I mean, otherwise you will, suppose you are designing the pollution control, or you are designing a stack height, let us say, you can even go back and do all the calculation to find out what should be the physical stack height, isn't it? If you know maximum allowable concentration is like this, then you can do the inverse problem and find out the H, right, which we people do. You know, people say, well, my maximum concentration should not exceed 100 micrograms. Then you said, well, all right, the worst ever is 100. Okay. Then whatever the wind speed, wind direction, you know, and this thing, and then you can go and find out the H by putting the worst maximum concentration here, right?
It's better to get that value which is having high frequency, not the maximum value. Better evaluate or
What do you say? What should we do? We should take the most frequent value, or we take the worst ever possible scenario? What, suppose you are an engineer, what would you do?
maximum value is having frequency very less, around one times per 10 years. But the minimum value, I mean, or some
Other value?
intermediate value is having a frequency of, let's say, around 50 times per 10 years. So what should be considered?
Okay, okay. See, normally it's very difficult to design something for worst ever scenario. We should not do that. Okay, there are stages of modeling. Okay, suppose something is proposed by, let's say, proponent, that we want to have such a power plant. NTPC comes to you, then you run through this calculation, okay, which is hypothetically maximum. Okay, suppose that concentration itself is very low. Okay, if this is very low, all others will be smaller than this one. Then you will say, power plant, don't do anything, just go ahead and build the power plant, right? Because under worst ever condition also, they are going to be not causing serious problem to you. Then you will not do any calculation, you will not do the computer, you will not do the sophisticated modeling. You don't want to find out the A, B, C, D, and because they themselves have proposed some H or some pollution control device. Okay, and that itself will contribute much smaller than what the maximum ever that you can think of. So then you don't have to do, don't increase your work unnecessarily. That's all right. Go ahead, come up with your plant. Okay, suppose that maximum, that concentration came out to be higher, or that thing came out to be this value, which was higher than this. Okay, then what you will do, you can run another analysis where you can find out the which set of the situation has the highest probability. Okay, then you came out with this situation is most likely to occur with probability of, let's say, you said 10 times in 50 times in 10 years. So then you say, well, all right, let's design the thing for this situation. And the designing part, how you can design the things, you can do, you have only two things in your control. Okay. The control you have is on this queue. You can ask them to control the pollution, you can ask them to use a better coal, okay. You can ask them to go for a better technology, okay. Or you can say increase the stack height. Both the things you can do. As an engineer, you will say, well, improve your Q or decrease your Q or increase your H or other variables, because you see you have to optimize the variables. Other variables you can say, well, suppose this, they say, well, we can't control, our coal quality is like this. Then you say, what about increase the H? They say we can't increase the H because civil aviation authorities, they come and tell you can't increase the H because there is an airport beside this one. So then what can you do? Then you will say play with this or play with this. So these are the options which people do exercise while designing for the pollution control or air pollution control. So see, they are the options you have. So for screening purposes, use this one, okay, to take a quick decision, yes or no. Okay, when you say nothing is required, fine. Well, something is required, then you do the further analysis of this table, or you say which situation is likely to occur more. Okay, I agree with you, because we cannot design something which occurs once in 10 years. Okay, once in 10 years, if that occurs, we cannot design for that one. But this is all matter of decision making, developing an argument, and argument comes always by virtue of knowledge, by virtue of understanding, by virtue of the physics of the system as you understand. So arguments can only be developed if you know the subject. Therefore, we say always you have to know the physics so that you can develop the argument. You may be either the side of the, let's say, a power plant, or side of a NGO, or the side of a government body. Everyone has their own point of view, and then you have to make decision making, and one person who will win the argument will be the one who has a clarity of the subject and has a good knowledge of the subject. Okay. We'll stop this discussion here, but you can appreciate as to how the things are done and how you can find out the maximum concentration. If you need more information onto this one, more mathematics part of this one, because I feel to give you more qualitative feel is more important than mathematical feel, because mathematics are there in the books. Sometimes with the books you don't get the qualitative feel of the things. So Sinfeld as the main our reference that we have given you in the beginning, Sinfeld will have more even equations and complications based on this. Okay.